Oh no. All right. Let me start. We're going to go over some of the R code for doing some of the modeling for water quality. So let's share screen here and R Studio. Okay. So this is, all right, this code here is what we're going to go over. So all this stuff here, these are all the packages eventually like we end up using. This is all in that GitHub link I sent everybody. Um, and this is something that we went over earlier, which is basically this chunk of code is to read in all the CSCI data, followed by reading in all the chemical data. And the only thing that's trickier with the chemical data is really this chunk of code here, which is basically doing a bunch of things in the dplyr package where you're taking the list of chemical analytes, which vary, like the number of ones we take at each site, and then make a standardized like table where each column is a chemical analyte. And if there just wasn't taken, we just fill it with Na. So that's the trickiest part. And then we merge it. So this is actually, this line here is where we got to last time. And some of this stuff we can go over, but some of it isn't necessary for how we're doing this, or it might not be, but this one here is just determine the number of samples of which each analyte was captured. So originally when I was kind of playing around with this, one of the things I thought was like, oh, well, maybe we don't want to include all the chemical data. Maybe we just want to only include chemical data if it was taken at like, some fraction of the number of samples. So like if, only take stuff that was taken at like 30% of the sample sites or more. But anyway, the way that works, even though like I kind of just thought like, let's just throw everything in. But the way this whole thing here works, but it may not be necessary, is just taking the streams data frame. And what this whole thing here is all right, so this is after the comma. So this is just all the stuff that you're only just filtering out by columns here, is take all the columns in streams, that's column names, streams, which happen to be in analyte names. And the analyte names is just the name of all the chemical analytes that we're taking. So I'm going to run this really quick just so you can start seeing like what this looks like in R. So I'm going to run this and it's going to think really hard here. By the way, stop me if like you have any questions with this. All right, so it's running, it's got to think, it's doing like thousands of calculations a second here. Okay. All right, and there we go. All right, so we have our streams thing, so 687 stream samples, and we have a whole bunch of different variables. So if we want to create analytes, it's just going to be the ones where it's the analyte frequency, where we're just going to say take the streams data frame and filter it so it's only those that have these column names. So when we create it, it's going to have the same number of rows as streams, but all the different number of columns. So I'm going to show you really quick. So 687 observations, same as here. Now it has 826 variables. So like we filtered out a couple of the variables that aren't actually like, like nitrate concentration or something like that. This command here says take the analyte frequency, and if it's greater than 0, make it 1. So this is literally just like, I'm just doing a quick what's called presence absence. Just say like, if there's a measurement there, just make it 1. Like all I'm doing is just marking that something was there. So like that. And this is column sums. What I'm going to do now is when you're doing column sums, you're going to take every row and you're going to collapse it and just add up all the numbers. And then I'm going to take that result and convert it to a data frame. So let's see what happens here so it's 687 observations, 820 variables. When I run this, there it collapses. And now it's just 820 observations of one variable, which looks like this, which is basically, we just summed up how often. So remember when I turned everything to 1, if you measured it, now when I just add it, that number is just going to be the number of times we took a measurement. So I just converted all the measurements that were non negative and just, or like just non-junk, and just said, hey, if it's there, it's 1. Um, and so this says like, oh, okay. Um, for example, like acid neutralizing capacity total, that measurement was taken 66 times. Alkalinity is calcium carbonate was taken 302 times. Okay. So this is a way of just kind of getting the frequency of it. And then I'm changing the column names here because otherwise it does this. Here, I'll show you again. Otherwise, it's just rename. It just names it like the column something, which is just kind of useless. And then I'm going to pass the analyte. I'm going to make a new column called analyte name, which is just the name of the actual chemical. So now we have 2 columns. Anyway, that's what it looks like. We might want to do filtering by how often things were measured, but I don't know. It was just something that I kept in there just like in case we might want to use it, but I think we might, it just won't really matter much one way or the other. Okay. What is more useful, or I'm still using, is this whole idea of looking at, we're also looking at watersheds and how often they're getting used. Um, so we look at, one of the things we could also filter on, and again, like we don't necessarily need to do it this way, but we can look at watersheds, and then we do this thing called table. So let me just show you like what table does. So we take this streams SMC shed, which is just going to be the column of like all the watersheds. It looks like this. All right. Basically, it's just like if we just drop that column out and here's all the information, it's like how often each watershed was involved in some measurement. All right. That's kind of a mess. But what you can do with table is it organizes it and says how often each one of those was collected. And it looks like this. So now if I highlight just table, by the way, as you notice, I'm putting functions inside of functions. So table now collapses and simplifies it. So now if you look at the result down here, it says Cayugas was taken 94 times, LA 65, Ventura 75. So anyway, you kind of get the idea here. Middle Santa Ana was only 2. So again, if we wanted to do this too, if we wanted to filter out things by watershed, we can do it that way. So in this case, now I'm making this one a data frame. So when I do watersheds, now it'll create a new watersheds data frame. That's just literally that. And then I'm going to rename the columns so it's a little clearer. So now it's just watershed name, how many samples are involved in it. Okay. So now if I just say like, hey, maybe I only want to look at watersheds where I have at least 60 samples. I just designated that. And now I can just filter it and say watersheds where the number of samples is greater than or equal to my sample minimum, which is 60. So now I do that. All right. Basically, all it does is it gets rid of Santa Ana because there's only 2. I kind of just did that because statistically, like it's really hard to do any sort of standard deviation or any other stuff if you have like that few measurements. All right. So now we can you can use that information to filter everything out. So if we look at this whole thing here, we have streams, these streams watershed. All right, we're looking at, this is to the left of the comma. So now we're looking at filtering things by rows. It says if the streams, the watershed names are in the watershed data frame that we made up here, keep them. So basically it's saying get rid of the Santa Ana watershed information because there's only like 2 in there. So now when we do that, you look at streams here, it says 687 observations. When we do that, now it drops to 685 because we just threw out 2 of them. And when we go to SMC shed, now I want to include, right now it's SMC shed. I want to convert it to a factor. And the reason is like later on when we do modeling, you want to say that the watershed's a factor and not a character string because it's how R deals with data and modeling. A factor is basically like an experimental group. So you want to treat your different watersheds as experimental groups because they're discrete data. They're not continuous numbers. So you can't really treat them as like a character variable. You have to treat them as sort of like a bucket that you're putting data in. So, all right. So now we do all that sort of stuff here. And now there's a bunch of things here where I have a bunch of data frames I'm initializing. I'm just leaving them blank right now. When you can initialize a data frame that's empty, it's just like a placeholder. So we're going to talk about what that means a little bit. What I'm going to do here is like you're making a loop. I'm going to set this number. So this is called set seed. Set seed is you're doing random numbers. Like for, let's say if you want, where we're doing subsampling here. but I want randomness in a way that is repeatable, which kind of sounds weird, but what computers do random numbers are not really doing random numbers. They're doing something that's called pseudo random. And they're basically, there's a kind of way that sort of shuffles the deck and away numerically that basically looks random. And if you say set seed and you designate the number, what you're doing is saying, like, all right, give me the same chunk of random numbers each time. So, like, yeah, they're random or quote unquote random. But more importantly, when I rerun this code, I will get the same results. Because if you don't, then, like, yeah, you always get a different string of like pseudo random numbers, which is kind of annoying. But that's why I'm just doing set seed, and you can put any number you want in here. I just usually just put one. Um, Now in this case, I'm just saying like, oh, sample num 100. So in this case, what I want to do is I'm going to randomly take 100 stream samples at a time and then run the random forest model using that data. And then in this case, I'm saying like, let's run it 200 times. All right. We can probably play around this. Like we might be, if we want, we can like probably bump this all the way up to like, 1,000 or whatever, or we can actually make sample num even bigger. Like maybe we can do 200 or 300. Um, However we want to do it. But anyway, this is just kind of like just playing around just to make sure this code even works. All right. So what does all this code do in the loop? So this is going to go run like, in our case, 200 times. So we make this data frame called stream subset. Okay. And what we're going to do here is stream subset. We're going to sample it. And when you do sample, what you're saying is the number of rows that I have in stream. So just take all the data that's in stream, shuffle it, and randomly take 100. So that's what the sample command does. And this is to the left of the comma. So these are just the rows. And so you randomly take 100 rows from the stream data set. That is now my stream subset. All right. And then what I want to do is I want to do this 5-way split. So this is that thing where you talk about like, we'll end up writing this in the paper, but this is like called, like this is like a k-fold split. And you can do this like k is some number. And it's really often that people do 5, like a 5-fold split. And what that means is you're making a group and you're making for modeling, what you do is you make a training set, which is this case, like you split into 5 chunks and you say, okay, take the one that's not 1. So that 20% in our case, because it's 1 out of 5, is the training is or sorry, the one out of sorry, the one that the ones that aren't 1. Sorry. So it's 2 through 5 out of 5. So it's actually 80% you're doing for your training set here. All right. And then the ones that the other remaining 20% are going to be your testing. And this is sort of a common split where people build, you take your data, you say, okay, 80% I'm going to build the model with, and I'm going to run it and on how well it works on the remaining 20%. And in our case, like what is it comparing against? In our case, it's comparing against the CSCI score. Because remember, we're treating our CSCI as the output of a model where the inputs are chemical analytes. So we have this 80%. So in our case, 80 samples go in. And the way we set up 80 samples go into building a model, and we test the results on the remaining 20. And then this line here, this one line, this is all the random forest we're doing. That's it. And so this random forest is just saying like, okay, run it. We're using a function called tuneRF. And what it does is it's just like it's running this on an input data frame. So that's what streams the training set here. And then we're going to evaluate, and then we have our output streams the CSCI. And we're telling it not to plot it. You can tell it to plot if you want. And then like basically this is an optimization thing. So if you want, I can show you really quick what this looks like if we just do one through on this. So I'm just going to designate, let's see, do we have, I think I initialized everything. Okay. So let's do streams. Oh, that's right. I didn't do not do sample num. Okay, so sample num is 100. All right. Now it should work. Okay, so now I made a stream subset. Notice here it's 100 rows, and we're going to run through streams train is 80, streams test is 20. All right. Now here it is. I'm going to run my random forest model. I'm going to call it RF1. The suppress warning thing here is like a thing you can do in R where sometimes like it'll throw like warning messages. It'll still run, but I usually just like don't want to listen to it. So I just put suppress warning on the outside. All right, so let's see what happens when I run it. Okay, so notice here where it says like all this stuff, where what it's saying here. All right, M try is 274. Basically, it's saying that it was able to make decisions based on the splits in 274 variables, or chemical analytes in our case, and the out of bag error was about 3%, which is really good actually. So what does this look like? Let's say if I wanted to rerun this really quick and I wanted to plot it true. So you kind of get an idea of what this even looks like. Oh no, you're looking at a graph from the other practicum. Okay, plot equals true. What does this even look like? All right. Oh, that's really boring looking. Okay. Well, I guess there's not much for it to plot because it's only one iteration, but it gives you a little bit more information down here. So yeah, number of variables tried at each split, 274. This model explains 42% of the variance here for this like one random instance. So, and by the way, remember I said on average when I was playing around with it, like I said, like, oh, on average, maybe it looks like 70%. That's on average. So we could have stuff that goes all the way up to like 100%, maybe down to 40%. So it'll vary, but we're kind of looking at the average. Okay. So this is me generating the model. Now, if I want to evaluate it, now we can run a thing. It's literally just called prediction, where we put our model RF1 in here, and now we compare it to how well it predicts what we see in the testing data. So now when we run this, all right, then we get this. This generates what's known as a prediction. So this say using our random forest model and using the chemical data in streams test, tell me what are the likely CSCI scores that should show up in the testing data. It's not the actual ones, it's the ones we're predicting. And then we can compare our prediction to the actual one. And we can do that because we can, what we can do is essentially look at what's something called the error function. And oh, these two things here, this is a whole thing where I'm taking like, because remember we're running this like hundreds of times, making a data frame and calling the column names are R, which is a Pearson correlation coefficient, and P is the significance. And we're throwing those into our data frame. We're actually throwing in our R score and our P values into that data frame because we're going to run this and aggregate it like hundreds of times. So that's kind of what this whole thing is here. But if we're just running it once, I just want to show you what this looks like. So error function, we're just doing the core dot test, which is correlation, in this case, the Pearson correlation coefficient, between our predicted CSCI scores and our actual CSCI scores. And what does our correlation value look like? It looks like this. All right, 0.73. Not bad. So, which is kind of like on average, like what we're sort of getting most of the time. And if we wanted to see the p-value, it's right here. And that's a p-value. That's really, okay, p-value of like, this is about 2.7 times 10 to the minus 4. That essentially means that there's like a 0.02% chance that our correlation is not just due to some random fluctuation. So it basically means we're probably seeing some real result, statistically speaking. So we take that information, we throw it into the data frame called RF evaluation. And then I have this other thing in here where I just make a data frame called RF evaluation total, which takes that result. And then it does this thing called R bind, which takes a data frame and you can just call row bind it, which means you're essentially gluing it top to bottom. So we're just making one row at a time and we're just gluing RF evaluation, which we calculate up here, and we're just merging it top to bottom to this one. So we're just building it row by row by row every time we iterate it. And we're doing something similar with the relative importance of the variables. So this is called RF importance. So the importance function, I'm just going to show you what that looks like when I run it here, gives you the relative importance of your variables. All right, it just barfed out a ton of stuff because we have like hundreds of variables. So this gives you all sorts of information for every variable, what their relative importance is. So essentially, like I can scroll all the way up here. Oh my God, there's so many of them. All right. So it gives you this thing, essentially increased node purity. The units themselves are not terribly important, but it's sort of like how it's determined. But you're more interested in relative importance, like which one, like what are the biggest numbers. So if I do this thing where I say, okay, take that number, throw it into a data frame, it's a little easier to look at. Okay, RF importance. Now let's open it up and see what it looks like. And if you want to sort things in data frames, you can just click on the column here. All right. So what this says is phosphorus is P is the most relative important. Like I said, the numbers themselves, this does not mean like 31.8%. This is just like, this is a number that deals with some like Gini coefficient split. But this says phosphorus is your most important variable. The watershed where you took the data is the second most. Chloride is the third. Phosphorus is P, which is separate than phosphorus is P total. They're actually different because it just depends on how you're counting things that are dissolved and things that aren't, and so on. And so we can kind of look at what the importance values are, but this gives you sort of this idea of like, okay, like what's the relative importance of all these variables, which is useful to know for the model. Um, Basically, it's saying like a lot of things that aren't terribly shocking. So like, well, this is actually one of the reasons we're doing it because like a lot of these things here come up really often when people do water quality. It's not showing you anything like really crazy. So um, and so this stuff here is to just deal with like, okay, like store all the importance values because you want to know that. And this next chunk of code here is to make something called partial response plots. So a partial response plot is a way of looking at how things vary between variables. So we talked about that a little bit on Monday. So like how it responds. Um, we wanted to, I guess, what this is doing here is for model variable, and this is like in the top end. So this is saying, like, look at my importance here. Take the top 10 most important variables, and then what you want to do is then go through each of those variables and then just make a plot, a partial response plot for each of them. It's essentially what it's doing here. And then this last thing here is then take all those plots and then bind them together. And that was kind of like that thing I showed you earlier with like all the plots arranged in a grid. So if we do that, let's see what happens here. So, all right. So if we do partial RF partial plots, oh, okay, never mind. Oh, that's right. Okay. So anyway, sorry, that's generating. It's not making the plots. It's making the data that we're throwing into the plots. So that's kind of why we have to make the heat map in the first place. So this is generating the code. This is generating the actual like XY coordinates for all the points you saw in those heat maps. And then later on, there's another chunk of code that outside of this loop once you've generated all that data, and then you can plot it. So anyway, that's all the stuff within the loop. If you want, I can run this. Actually, probably should just run this a few times to give you an idea of what this looks like in operation. So let's see, this is sample num 100. Let's just do like, I'll run this 10 times. All right. And let's rerun everything just to make sure that I don't have anything left over. Okay. All right. Now we're going to run this. Okay, so now as you can see, like each time it goes through the loop, it's doing this whole thing where it's thinking like, okay, all right. And by the way, the out of the bag error will be slightly different each time because you're dealing with like a different set of 100 samples. All right. Anyway, so any questions on this right now, other than like I just threw all this at you?
I mean, I have don't have any like super specific questions just because I need to probably like go back through this again. But how long does this usually take to run through?
Well,
Like,
that's why I just want to show you like how long it takes to run 10. Oh, now it's done. Okay.
mm,
To give you an idea, if you're running only like 100 samples at a time, um, if you're running like 100 samples in a group, it takes to do 10, it takes like a minute. To do 100 takes like 10 minutes. So, um, it depends on like, I mean, we might, if we want to do something like more involved with like 300 samples at a time, then it might make sense for me just like to throw it on a remote computer to run it. Um, this kind of code actually will run, but if you're up to like 300 samples, it'll just like probably run, it'll take hours on a laptop. So, but if we kind of go through and like look at, so this is, I generate all these data frames down here. So we look at like RF partial plots. I just want to show you what this looks like here. But now it's made like, this is the actual data, ammonia, the CSCI. Yes, the ammonia, CSCI is ammonia. And then like, basically this is the actual data that's going to get plotted. And there's a lot of NAs because there's a lot of just stuff where like, there wasn't information that was needed for it. But this is the actual stuff that gets thrown into making plots, those heat maps for the partial response plots. The RF importance. So if like we look at the relative importance, yeah, again, so let's sort this here. Yeah. So it's not the same every time. So in this case, the watershed for that 100 samples was the most important. But this is actually one of the reasons why we kind of want to run through and do tons of iterations on this just to start getting an idea like, well, on average, what does this look like? So
So when we set the seed to like the same number and then we iterate it over and over again, the same set of random samples for each 100 is chosen. Is that correct? So you get the same kind of overall result, the same, but it's still random.
yeah, so it's just kind of like picture. It's just like you were just it's just saying like, oh, I'm going to generate this random string of numbers. It's going to be this long, but just use that every time. So when I rerun this code, you'll generate your loop and you'll get a different set of random numbers within the loop each time. It's just that for that 10 times you run the loop, you'll have that same repeated stretch of 10 like random sequences. So it means it'll be reproducible, basically.
So those same like 100 samples, those are the same every time. Like,
No, within
or
the
no.
loop, within the loop, you're going to be taking like a different 100 each time. It's just that you'll have like that, but when you rerun it, you'll have that same group. Like it'll be the same like 10 groups of 100 random samples each time.
Okay, I think that's
Yeah.
what I was thinking
Okay. Yeah. Yeah. So it's not just doing like the same 100 over and over again. It's like a
of.
different 100, but it's just like going to be the same overall pattern if you set seed.
Okay. And then I had a question of what the importance was measuring exactly when you.
It's so if you actually here you can, if you do question mark, once you install the package, you do question mark importance, it'll go through and it goes in a bit of it. Basically it's doing a something called node impurity measured by the Gini index. Trying to think of a good way to like a concise way to explain it, but it's essentially a measure that if you were to um, remove that variable from your decision tree, how much it throws your results off by on average. So if it makes a big difference or a little difference. So it's
Okay,
like,
that makes sense.
yeah, like that's probably the quickest way to explain it. Like, but it gets kind of, yeah, that's one of those things where it's like, it always seems kind of hand wavy, but it's just a version of like, if you don't include in your model, does it throw everything off by a lot or a little, essentially? Cool. So this is like the code that's in the loop. There's like more code after this, but this is like to start getting to the point where you can run your model and then you can aggregate the results in terms of like the correlation coefficient, its significance, and then the relative importance of the variables for like each iteration of that model, which is going to be kind of like really important for when we try to evaluate what's going on. So. You okay if I stop share? Or do you want me to keep it on?
You're good.
Okay. Awesome. All right. Cool. So I guess anything else before I stop recording, or what are you thinking?
For the partial response curves,
Uh-huh.
is there the code to plot that, or is that a separate thing? Did we
Oh no,
cover
it's I have that.
that? Okay.
Yeah, we can go over that like another time. That's just more of, I haven't put that in there yet because I'm kind of debating on like how I want to do that. Because I've structured it in a way that was trying to like force everything to like 2x5, but R does some really wonky things with the graphics. And I think I just want to dump them out as like individual plots. And then like, that was actually something I was going to talk with Ayana about, was just like, okay, here are the individual plots, like stitch them together in a way that doesn't look like crap, because R keeps making it look like crap. So that's why I haven't like thrown the code in there, because it's probably not necessarily going to be useful. Even the stuff with like the watershed and analyte frequency stuff, like, I don't know. It's not like really as key as I thought it was going to be, because the thing is, when you run a random forest model, you can just like throw everything in there, and if it's just not important, it would like basically it comes out in the model. So you don't really need to filter it out earlier. Cool.
Yeah, I don't have any other specific questions right now, but I'll probably email you with those
Okay.
over the like tomorrow or over the weekend, because I'm gonna spend some time tonight going over what we just reviewed today.
Yeah, I mean, I know I just barf this all out. Like there's no quicker way. Like just play around the code I sent so far. I'm trying to like at least just give an overview of it, but hopefully this helps, and the comments in the code help. But yeah, like,
Yeah, the comments are really helpful.
thanks. If you want me to put more comments in there, let me know. It's I can do that, but I'm not altering the code on the GitHub yet, because I don't want to throw people off on it. So just play around with it. Like there's no shortcut around it. You just kind of have to play around with it.
I was wondering, for the GitHub, when I
Yeah.
download it, it makes me download the whole entire package, so or like all of the individual
Oh, okay.
things. So
This is gonna sound, yeah, okay. So that's like, yeah, because people a lot of times like they just do GitHub as they'll do as a package. Believe it or not, this is how I do it. I literally just like highlight all the text and I copy and paste into my RStudio.
okay,
I'm sorry, I should have said that earlier.
yeah, that's better.
I know, like, when people do this, a lot of times they'll do it to build packages, and like you just download the whole thing as a unified package. But yeah, for what we're doing, we're just basically using like Google Docs for code. You know, I'm not building a package with this. I'm just storing scripts. So, but yeah, thank you for pointing that out. I'm not a power user of GitHub. I've just been using it at this level for like 10 years. So cool. Well, I guess I'll stop recording here.